guys. This video cast is going to cover the basics of chemistry and specifically some information about water that I'm hoping most of you are going to be able to bring forward from your experiences in biology and in chemistry. So this is kind of our introductory unit, and it's mostly review. All right. So if you see me looking down, I'm controlling this from my cell phone. A good place to start is how science in general approaches the study of biology. And you have to keep in mind that physics and the laws of physics control everything, all aspects of matter and energy. Chemistry is a specific science that looks at how and when compounds and elements form and the periodic table and all of that stuff. And biology, finally, focuses on living matter. That subset of matter that has this characteristic we call life. And that's actually a really complicated topic. But for right now, what I want you guys to see is that you have to know a little bit about physics to understand chemistry, and you've got to know a lot about chemistry to really understand biology. Okay, so keeping that in mind, all right, moving forward. Come on, click forward. You may have heard some people say that, physics is the only thing that matters and everything else is stamp collecting. I believe that's originally a Richard Feynman quote. It's something I think Mr. Hubbard still has on a bulletin board somewhere in one of his classrooms. But if you see him in the hall, tell him that biology is not just stamp collecting, and see what he says. I think that's kind of funny. All right, so good place to start when you talk about the role of chemistry in biology is you really have to know the difference between elements and compounds, okay, which I'm hoping that you learned in middle school. So how do you know you're looking at an element and not a compound? Okay, well, elements are made up of only one type of atom, and atoms are classified on the periodic table by their proton count, okay, or what we call their atomic number, all right? So every element has an address on the periodic table. I'm not even going to pull one up here because that's not really what we need to focus too much on in biology. All right. Compounds, on the other hand, are made of elements that have combined chemically, either covalently or ionically in a bonding situation, and the proportions are set. So every compound, every chemical compound has a proportion like H2O, 2 parts hydrogen to 1 part oxygen, that if you change that proportion, you change the compound. All right, what else do we need to know here? So in chemistry, the part of chemistry that we really need to know a little bit about for biology is what are the elements that are involved in the building and the operation of living systems. And so we can break them basically down into 3 categories. Okay, there are the essential elements of life, and there are only 4 of them. Okay, we call them the big 4, and they are carbon, hydrogen, oxygen, and nitrogen. Okay, there are 7 other elements that frequently show up in biochemical pathways and the biochemistry that keeps life running. And I'm gonna share these with you as their chemical symbols: calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium. Okay, so here we got 7 plus 4, that's 11 elements. And just so that people don't squawk at me here, there are others that play really minor roles. We can call them trace elements, stuff like boron and zinc. Yeah, they are involved in living systems, but when those come up, I'll tell you about them. We don't really need to focus too much. So the purpose of this part of my presentation, you can ignore pretty much the entire periodic table with the exception of these 11 elements, okay? All right, so let's look at a case study. So let's imagine that we are exploring how life adapts to the presence of toxic elements. Okay, so let's look specifically at what happens when you irrigate farmland, which means the only reason a farmer is going to pay money to pump water onto his crops is if it doesn't rain enough. Okay, but there's a big difference between rainwater and irrigation water. All right, so I want you guys to think, if irrigating cropland causes the levels of salts in the soil to increase, where are the salts coming from? All right, could you maybe answer that question? I'm going to answer it for you, but I want you guys to start thinking a little bit like this. So, and what effects will these salts possibly have on agriculture? All right, well, let's answer them. If you're irrigating crops, you have to pump groundwater. And groundwater is simply rainwater that's worked its way down through the soil into some underground aquifer or some underground layer, and the farmer pumps it out. But as the rainwater moves to the soil, it's going to be picking up minerals and other compounds that are dissolvable, that are soluble in water. And when those are then sprayed on fields or irrigated onto a field, and the water evaporates, those compounds remain behind. And a lot of those compounds are what we call salts, and a lot of them are not good for plants, especially if they build up to a certain level. So how might this affect agriculture? Well, we need to breed new varieties of corn and wheat and rice and other crops that can tolerate irrigation over decades and decades and decades. If you do just a quick Google search, you will find lots and lots of examples of irrigated farmland in the Southwest and the Midwest and in in California that are suffering from selenium poisoning and boron poisoning and regular old table salt poisoning. These are coming from the buildup of salts because of irrigation over the last 100 years. So just an example, case study in how compounds and elements might affect biology. All right. Okay. Next topic, isotopes. This is a word you're going to see in at least 4 different places this year. Isotopes, if you remember, are special conditions, so to speak, or special types of elements, and they have importance in biology. Okay, so let's look at some things here. Isotopes are just atoms that have the same number of protons, but a slightly different number of neutrons. Okay, so for example, you can have an isotope of carbon, regular carbon. The most common isotope of carbon is carbon-12, but you can have carbon-13 and carbon-14. 13 has an extra neutron, and 14 has 2 extra neutrons compared to carbon-12. Now, where it gets interesting is carbon-14 is radioactive, which means it won't stay carbon forever. It will spontaneously break down into other elements. Okay. Now, the rate at which carbon-14 breaks down is a characteristic, is a property of carbon-14, and that's known. So you can graph this, and you can use the disappearance of carbon-14 in a sample of charcoal or a piece of a mummy or something like that, and you can use the graph to figure out how old that sample is, because the amount of carbon-14 in any living body, once that body dies and stops putting in more carbon, that the amount of carbon-14 steadily declines over time, and that rate is known. So isotopes are important in biology for dating things. Also, there are some other uses in experiments we're going to talk about as they come up. All right? Okay, another topic from chemistry that I'm hoping you can bring forward, the idea of energy. All right, so there are different forms of energy in science. There's potential energy, there's chemical energy, there's kinetic energy. Chemical energy is just a type of potential energy. Kinetic energy is a little bit different. So let's look at all of this stuff. Okay, I'm just putting them up here. Let's take them one by one. So potential energy is energy that's stored away, usually in a chemical in biology, and it's available to do something with, to make something happen. Probably the most familiar way of measuring potential energy in biology is the calorie. Okay, a calorie is the measurement of energy in food that you're probably familiar with. Chemical energy includes potential energy, and it's any kind of stored away energy that is stored in chemical bonds. That's where it's actually located. All right. Kinetic energy is different. Kinetic energy is the energy that exists when molecules or atoms are moving. Okay. Now we know this as heat energy, and you can measure the average kinetic energy of a sample by taking its temperature. All right. So temperature is important in biology. Calories are certainly important in biology. So you need to know a little bit about this concept of potential versus kinetic energy to understand and apply to biological concepts. All right. Energy in atoms and molecules is related to how far the electrons are away from the nucleus. So the farther away from the nucleus the electrons are existing, the more energy they can hold. And the ones on the outside, the valence electrons, the outermost shell, are often the ones that we're most concerned with for chemical bonding. Now, for biology, well, man, we're not going to go very deep into this at all, but we will talk about uphill and downhill type chemical reactions when we get to metabolism. All right, so chemical bonds. The stronger types of bonds, the ionic bonds and the covalent bonds, are what hold compounds together, and they're what give compounds their proportions, like H2O, CO2, information like that. Chemical bonds can be polar or nonpolar. Okay, so nonpolar versus polar covalent bonds, that's important, especially when we get to water. All right, and finally, ionic bonds. Oh man, the only time that really comes up in biology is when we talk about salts, the way salts dissolve in water. Sodium chloride is held together by ionic bonds. All right, so most importantly, a weaker type of bond, the hydrogen bond, that's going to be more important. And we're going to focus on that when we look at water molecules. Okay, and finally, van der Waals interactions, which van der Waals interactions are remarkably difficult to put into words. As a definition, the best way I can explain it to you is with an example. So let's go through these and then we'll get back to van der Waals interactions. Okay, so hydrogen bonds, as I said earlier, are really important to understand water. And hydrogen bonds hold water molecules together. They happen because within the water molecule, the bonds that are holding the hydrogens to the oxygens are what we call polar covalent bonds. And those polar covalent bonds create differences in charge in different regions of each water molecule. So this basically makes water molecules very sticky to other water molecules and to other compounds. All right. Van der Waals interactions are also attractions between molecules, but they can be between any molecules because man, I don't have the physics to really explain using the technical terms, but electrons are always moving. They never sit still. And at any given time, electrons can clump up in an atom or in a molecule, and this can create areas of positivity and areas of negativity that make different molecules attract each other. And a good example of this that was recently figured out, this animal I just put a picture of up is a gecko. A gecko is a type of lizard. And the thing that's really cool about geckos is they have really, really sticky foot pads. And I read somewhere that geckos can actually run up vertical walls and across ceilings completely upside down using their sticky little foot pads. And their little foot pads are so sticky that the entire weight of the animal can be supported completely upside down with one toe. So scientists were very curious about how can this little animal have feet that are so sticky but still unstick so the animal is not permanently locked in place. And what they found out, it's van der Waals attractions or van der Waals interactions. The foot pads have evolved these very, very, very small filaments that allow, because they're so tiny, these filaments can get very, very close to the molecules of glass or stone or wood so that van der Waals interactions can actually come into play and make that little foot pad sticky. But these little filaments are arranged in a way so that the animal lifts its foot in the right direction, it can disengage these interactions and then re-engage them very quickly. So this little animal can scamper across surfaces and ceilings that it seems like they're defying gravity. But it's just physics, which is kind of cool. All right. Reactants versus products and chemical reactions. All right. Another important concept. I know everybody in AP Biology is supposed to have taken chemistry, and I know you guys had a unit pretty much where you learned how to balance chemical reactions. So you had stuff on the left, an arrow, and stuff on the right. So I want you guys to bring that forward to AP Biology. Reactants are generally written on the left side of the arrow. Then the arrow points to the right, and on the right side are the products. So a chemical reaction basically reads from left to right. Reactant A and reactant B and reactant C interact with each other to produce, on the other side, the products, which, can vary depending on the type of chemistry. Chemical equilibrium is the point where the forward and reverse reactions offset each other. So chemical reactions don't just go to the right all the time. They can be made to reverse themselves. And the conditions that regulate how and when this happens are all part of this concept of equilibrium. And that's important in biology because equilibrium, chemical equilibrium, is dynamic, which means it changes depending on local conditions. And local conditions can include pH and temperature and salinity and how wet it is or how dry it is. All these things can affect which way a reaction will proceed, which way the equilibrium will settle. So that's an important idea in biology, especially in metabolism, which is going to be our next unit. All right, good place to stop, look at something visual. Hope you guys recognize this historic picture. This airship called a Zeppelin was the Hindenburg, the Hindenburg, the flagship of the Zeppelin fleet, put in the air by Germany in the 1930s. And the cool thing about Zeppelins is they kind of float because they're filled with gas that's less dense than the atmosphere. Now, Zeppelins originally contained helium. Helium is an inert gas. It won't burn. But in the years leading up to World War II, Germany had trouble acquiring helium for various political reasons. So they filled their very large Zeppelins with hydrogen gas. And they were confident they could control the number one problem with hydrogen gas. Now, hydrogen gas, if you guys remember, I want to try to write it up here. Hydrogen gas is H2. It's a diatomic molecule. It's made up of 2 atoms of hydrogen. And hydrogen gas is flammable. It's explosively flammable if it can mix with oxygen. So if you mix hydrogen gas with oxygen gas, which is another diatomic molecule, O2, a chemical reaction will happen. That's what the arrow means. And you will get water. Okay, so basically, hydrogen gas wants to combine with oxygen very much to produce water. And that's what happened when this accident took place. The Hindenburg caught on fire. What caused the fire? Not really for sure. I don't think anybody knows for sure. Could have been lightning, could have been static electricity, but the whole thing went up in flames, and all the hydrogen gas that was inside of those giant bags inside of that metal framework converted to water and released massive amounts of heat and light energy, and water was produced. So I like to use that picture to show a very simple chemical reaction. Now, if you're paying attention, if you paid attention in chemistry, there's something wrong with this chemical reaction. It's not balanced. So how would you balance it? Well, what that means when we say balancing a chemical reaction, in a balanced chemical reaction, everything on one side has to be represented equally on the other side. All right. So in this chemical reaction, you can see on the left, the reactants, we have 2 hydrogens. And on the right side, with the product, we have 2 hydrogens. So we're balanced for hydrogen, but we're not balanced for oxygen. There are 2 oxygens on the left, but only 1 on the right. So the only way to make this reaction balanced is we have to add some coefficients. So if I add a 2 here and a 2 here, I think we're now balanced. So we have 4 hydrogens on the left, 4 hydrogens on the right, and 2 oxygens on the left and 2 oxygens on the right. So we balanced it. So just a quick little review there about, it's always important when you write chemical reactions that they're balanced. All right. Okay, on to the properties of water. Water molecules are interesting for a couple different reasons. First of all, as far as we know, all life on Earth depends on water. So water is a big deal in biology. And water molecules have polar covalent bonds holding them together. So this polarity of the bonds causes hydrogen bonding. Okay. Now remember, hydrogen bonding is the ability of water molecules to attract and stick to other water molecules. Now this stickiness causes cohesion, which is when water molecules stick to other water molecules, and adhesion, which is when water molecules stick to other stuff. like glass or hair or soil or anything that is also able to form hydrogen bonds. Now, this cohesiveness and adhesiveness of water produces some phenomena that are important to biology. Phenomena such as surface tension, capillary action, heat capacity. There are others, but there are three. There are three right there that's enough to get us where we need to go. And these phenomena have huge effects on living systems, like the ecosystem of a pond, or the life of a plant, or producing local climates and local microclimates. So let's look at each of these in a little bit more detail. All right, so here is the classic picture of a, hold on, I lost my connection here. Let me get back. All right, here is your classic picture of a water molecule. Right here we have H2O, looks like Mickey Mouse. It's got a red oxygen atom polar covalently bound to two hydrogen atoms. Okay. Now, if you put water molecules together, they form hydrogen bonds. So if you look over here in this picture, you see dotted lines. Those represent hydrogen bonding between the relatively negative oxygen end of each water molecule to the relatively positive hydrogen end of another water molecule. Okay, so I'm hoping that shows you pretty clearly what hydrogen bonds are. All right. Now, why is this important? Well, hydrogen bonding makes water very cohesive. So water molecules want to clump together, and they especially want to do this most strongly at the surface or the interface between liquid water and atmosphere. And so this produces a phenomenon in nature called surface tension. And this little insect called a water strider actually spends its adult life scampering around on the surface of water. Its little feet can't get wet. They will not form hydrogen bonds. So this little animal can actually skate across the surface of water while its prey is not able to do this. So this animal is literally a hunter. It's sensing vibrations in the surface tension and using it to track and find its prey, okay, which might be like a moth or something that gets caught in the surface tension and can't skitter across it, all right? Another phenomenon produced by hydrogen bonding is capillary action. Capillary action happens when water molecules climb upward against the force of gravity. Now, on the left-hand side here, we have a very simple experiment you can do at home. All you need is two glasses, some water, and a paper towel or some toilet paper. Just put some water on one side, put the paper between the two glasses, and it's slow, but it will happen. The water will creep upward against the force of gravity, soaking into the paper, because paper is made of a material called cellulose, which is very hydrophilic. It attracts water molecules. It is very adhesive to water molecules, and it will literally pull chains of water molecules uphill over the rim of the cup and into the other side. So if you let this run until equilibrium, the water will be at the same level on both sides, given it enough time, because of capillary action. Capillary action just happens because of physics. Now over here on the right, this is more of diagrammatic. This is showing you how water will literally climb up the sides of really thin glass tubes, because water is adhesive to glass. And so the water molecules will actually move upward against the force of gravity. And the narrower the glass tube, the farther they will move. So if you make the tube narrow enough, you can actually make water travel great distances uphill, apparently against the force of gravity. And this is actually how plants are able to absorb water without exerting hardly any energy at all from the soil up into their leaves. Okay, this is because of capillary action. So these are two examples of two properties of water that happen because of the polar covalent nature of the way the electrons are distributed inside of a water molecule. Okay, heat capacity or specific heat. I'm going to, for this class, use these terms interchangeably. That may not be technically correct from a chemical or physical point of view, but heat capacity or specific heat just references a property of water. Simply stated, is water is really slow to heat up and really slow to cool down. So if you expose a body of water to sunlight and some land okay, some, like say a beach, to the same amount of sunlight, the sand will heat up a lot faster than the water will, because the water is absorbing energy, the sand is absorbing energy, but the water needs to absorb a lot more energy before its temperature changes. So that means water has a very high heat capacity compared to just about everything else. So this has amazingly important ramifications to climate. All right. That means that large bodies of water heat up really slowly in the spring and summer, okay, and then cool off very slowly in fall and early winter. So this has a moderating effect on climate. So if a land environment is close to a large body of water, it will experience a much less severe temperature swing over the course of a year than an area of land in the middle of a continent, for example. All right. Okay, so here's a list of the properties of water that we have talked about. I've saved the best for last, pH. pH is incredibly important to living systems. pH is a number that is a property of an aqueous solution. So any solution that's made of water is going to have a measurable pH. And I'm hoping you guys remember pH basically comes in 3 flavors. You can be acidic, you can be basic, or you can be neutral. Now, I don't have neutral up here. Acids have pH that is lower than neutral. And of course, neutral is 7 on the pH scale. Bases have a pH that's above 7. So when you say that a chemical is acidic, that means when you mix it with water, it makes the pH go down. And you say a substance is basic or alkaline, when you add it to water, it makes the pH rise or go up. Now, buffers are chemicals that if you mix them with the water, it makes that solution resistant to a pH change when you add acids or bases to it. And buffered solutions are really important in wet chemistry and biochemistry, also really important inside of your body. And we'll talk about some buffers you have in your blood later on when we get to that part of metabolism. Now, what are the numbers about? Well, technically, the pH reading you get is actually a logarithmic calculation. It's the negative log of the concentration of hydrogen ions in the solution. And why is that? Well, if you guys remember, water is H2O, and water will dissociate rarely into a positive hydrogen ion, H+, and a negative hydroxide ion, represented by OH-. Okay, now, when each water molecule dissociates, that means it produces one hydrogen ion and one hydroxide ion. So it's a balanced dissociation. So that means the concentration of each of those ions is the same. And it's a very small number, 1 times 10 to the negative 7, right? So it's very, very, very small amount, okay? So why is that important for AP biology? Well, we're going to need to play around with pH in some situations. So let's look at this first example. If pH is 7, which I said earlier was neutral, that means that the hydrogen ion concentration is 1 times 10 to the negative 7, which is equal to the hydroxide ion concentration, which is also 1 times 10 to the negative 7. So that's why a pH of 7 is neutral. It's right in the middle. The ions are balanced. Okay, now if we raise the pH to 8, okay, now remember, a pH of 8, anything higher than 7 is going to be what we call basic. Okay, so that means the hydrogen ion concentration has to come down, has to decrease. So you'll notice that the hydrogen ion concentration is 1 times 10 to the negative 8, which is a lower or smaller amount than 1 times 10 to the negative 7. But interestingly, the hydroxide ion concentration has increased. It's now 1 times 10 to the negative 6. And if you notice, 8 and 6 add to 14. Okay, so that's where the numbers of the pH scale come from. All right, so if you look at the third example, if we lower the pH to 6, which takes it down into the acid range, notice that the hydrogen ion concentration has increased to 10 to the negative 6. It's become 10 times higher, whereas the hydroxide ion concentration has decreased by a factor of 10. So all I want you to see from this slide is the pH scale is based on some math, okay? The math involves logarithms, which I don't think I'll ever mention log scales again in this class, but the pH is related to the hydrogen ion concentration. The more acidic a substance is, which means the lower its pH, the more hydrogen ions are present. Okay, so it's an inverse relationship. And if you know the pH, you can actually figure out the pOH, or the concentration of hydroxide ions, because they always have to add to 14. I'll stop there. That's as deep into that math as I really, really want to go. All right, so I think that is the end of the slideshow. We will stop there. Thank you guys for listening, and if you were absent from class, I made this video cast for people primarily who weren't here or people who need to review. So we will go over this in class and you'll have a chance to answer questions. Thanks for paying attention, and I'll see you guys later.